Hello, I'm Nick Paradiso. I'm Conair's product manager for their conveying product line, and I'm here to talk about wave conveying. Wave conveying is industry-disturbing technology that truly allows you to convey your resin up to 3 times slower, but still you're able to make rate with respect to dilute phase conveying that you're familiar with in your plant. What I show on the screen now is a very important equation that allows me to illustrate how important wave conveying is with respect to what's going on in your production facility. Attrition and erosion is directly proportional to velocity of the resin to the exponential degree. Attrition is going to be applied to your resin, the attrition of your resin, the breaking down of your pellets with respect to dust generation or angel hair, and erosion is going to be based on system components. If you're conveying glass-filled nylon, for example, and you're wearing through elbows or you're wearing through receiver bodies, and you're causing problems, that's because you're conveying that resin too fast. You don't have to. You do not have to have your system be within the dilute phase of pneumatic conveying. You can implement wave conveying to be able to slow that resin down and still make rate at your receiver. To compare wave conveying to dilute phase conveying, I have on the screen now a quick representation of the difference between the two. So we understand that Boyle's law tells us that pressure and volume, and in this case we're going to take a dynamic understanding of this, so pressure and volumetric flow rate at the pickup point must equal pressure and volumetric flow rate at your receiver. And furthermore, back at the pump and anywhere in the line you can take this understanding, but from a macro view we're just going to look at the pickup point to the receiver because that's the profile, the speed profile that resin is going to see throughout your pneumatic conveying system. With dilute phase conveying, you're at atmospheric pressure at the pickup point, and you're looking at around 10 to 12 inches of mercury, or maybe more, slightly less than that, but call it 10 inches of mercury at your receiver. So you're seeing a fairly high delta P, delta pressure. Really, it's negative in this case, but it still applies for both sides. You're seeing a pretty high delta P here, where when you translate that to balance the equation out, that results in a very high delta V, so delta volumetric flow rate. And in this case, if you divide by the cross-sectional area of your conduit or of your material handling line, you can understand that you pick up the material at a very high speed and it's only going to accelerate towards your receiver. It doesn't slow down ever in your conveying line. You're always going to be accelerating and increasing your velocity from pickup point to your receiver. Now, this requires a continuous high pickup velocity when you're in dilute phase. The reason being is you have to continue to pick up resin into your material handling system while holding true to an industry standard of 3,500 to 4,000 feet per minute of pickup velocity. That is required because resin is sitting in its storage, in its bulk storage state. If it's in a silo, if it's in a surge bin, if it's in a gaylord, however that resin gets to your facility, it's sitting there and it's not moving. Its velocity is 0, quite frankly. When you put your wand into your gaylord, for example, that air that's entering at the end of your wand has to be high enough to pick the resin up into the line to get it moving. And it has to be continuous because you're always going to be conveying that material. That high pickup velocity must be achieved while still conveying resin throughout your whole material handling line, and that's where pump sizing and other variables come into play for your pneumatic conveying system. Now, how wave conveying works is we operate in a very deep vacuum state. And when I say that because we're choking down and we're controlling, quite frankly, we're controlling the air that's allowed to enter the material pickup point. And inversely, to balance the equation, the same equation used for dilute phase applies here for wave conveying. In order to balance it, we have a much lower delta V, delta volumetric flow rate, which can be translated to delta V of velocity. And this allows us to have a much lower pickup velocity. The best way to illustrate this is a vacuum cleaner. So industrial pneumatic conveying systems in the plastics industry are just very large vacuum systems. So imagine you have your vacuum cleaner at home and you take your hand over the edge of the probe or of the tube and you cover it about 75% of the way, for example. You'll start to feel the suction on your hand. Maybe your skin pulls into the end of the vacuum probe. Now, if you take your hand, you remove it from the probe, put it back down, remove it, put it back down. What you're doing there is you're breaking a deep vacuum state. You're breaking a vessel within vacuum. You're breaking that to atmospheric pressure. When you break vacuum to atmospheric pressure, you have an inrush of air. Physical air has to enter that line, enter your vessel or enter the material handling line in this specific case to be able to alleviate that pressure differential. What we're doing with wave conveying is we're getting the material picked up by achieving that 3,500 to 4,000 feet per minute, but it's not continuous. Our patented technology allows us to pick material up in cycles and keep it moving very slow. So low pickup velocity with respect to that first acceleration zone of your material handling line, and keep that material moving extremely slow throughout the full conveying to your receiver. Now, wave conveying requires deep vacuum. Deeper than what a positive displacement pump can achieve. So our HRG pump, and on the screen I show our LDP pump, allows us to convey at a much higher vacuum, up to 20, maybe 20 inches, 21 inches of mercury, depending on your application and your conveying distances. We also utilize VFDs on our pumps. So once you get your wave conveying system in phase, we can use the VFD to slow it down and keep it furthermore controlled within wave stream or wave pulse to get speeds as low as 300 feet per minute of moving your resin. What I show on the screen is a quick cross-sectional image of what dilute phase conveying looks like, wave stream and then wave pulse. Wave stream is the optimal negative pressure pneumatic conveying system. I say that because you're able to get the maximum amount of throughput through that line at the lowest amount of conveying speed. Notice dilute phase conveying is very lean. It's a lot of air, a little bit of material. Wave stream has the optimal amount of pellets with respect to what throughput you're looking to achieve. If you're running an apples-to-apples comparison, count the amount of pellets that are in the wave stream image compared to the amount of pellets that are in the dilute phase image. Even though dilute phase you may be conveying 2 or 3 times faster, imagine achieving that same throughput or greater by conveying slower and not causing your dust, your angel hair, your component wear in your system. Wave pulse technology is going to be for your specialty applications. This is a phase where you're going to have very dense, very thick slugs of material with air pockets in between them to keep that material moving. Where wave stream is going to be, really could be applied to any pneumatic conveying line today by applying this wave technology to your system. What I show on the screen here is a quick speed chart to show the difference between dilute phase, wave stream, and wave pulse. The numbers on the chart represent pellet speed. Now, 3,500 to 4,000 feet per minute of air velocity is required to pick the pellets up into the line, but the pellet velocity is going to be about 80% or so, 75–80% less than the air velocity to start. Those pellets start to accelerate through the system as it gets towards your receiver, and that slip factor or that D rate from air to material velocity can get up to about 95% or so before the pellets enter the receiver. What we show here is dilute phase conveying is extremely fast conveying with respect to pellet velocity. Wave stream will terminate, and by terminate I say the pellets will enter the receiver at a speed slower than where dilute phase conveying is even picking up the pellets. That's how powerful this technology truly is. Now I put this slide shows the equation that we talked about in the beginning of this presentation that shows that attrition and erosion is directly proportional to velocity to the exponential degree. So imagine you're conveying with dilute phase conveying and your terminal velocity is 5,000 feet per minute, where with wave conveying your terminal velocity is 2,000 feet per minute. What does that do for your dust generation, your angel hair, or your system component wear? It's exponential, as you can see here.